Light does not move. You look at a light bulb and you naturally believe the light leaves the bulb and travels to your eye. In a small room, that trip is so fast you never notice the delay. But you know, it must take some time. Replace that bulb with the sun and everyone knows the number. About 8 minutes before sunlight reaches Earth. It feels obvious. Light leaves the source, crosses space, and arrives here. But nature has a strange habit of ignoring what we call common sense. From the point of view of the photon itself, nothing traveled and nothing passed. If you could ask a photon how long it took to go from the sun to your eye, the answer would not be 8 minutes. The answer would be 0. If you asked how far it traveled, the answer would also be 0. In the deeper geometry of space-time, the moment the photon is emitted and the moment it is absorbed happen at the same instant for the light itself. The star and your eye are connected by a bridge where time does not pass. Now let us begin with something very simple, something so familiar that nobody ever questions it. Imagine I am standing on a field with a baseball in my hand. I throw the ball forward as hard as I can. Suppose the speed of the ball relative to me is 100 miles per hour. If you are standing still on the ground watching the throw, you measure the ball moving at 100 miles per hour, everything is perfectly reasonable. Now imagine that instead of standing still, I start running forward before I throw the ball. I run at 10 miles per hour, and at the same moment I throw the ball forward at 100 miles per hour relative to my hand. What happens to the speed of the ball that you measure from the ground? According to everyday physics, the answer is simple. My running speed adds to the ball's speed. 10 plus 100 gives 110 miles per hour. This is the rule that governs almost everything we experience. Bullets fired from moving trains, balls thrown from moving cars, even a person walking forward inside an airplane. Speeds add together in a straightforward way. The faster the source moves, the faster the object appears to move to an outside observer. This idea is so natural that it feels like a law of common sense itself. For centuries, scientists believed that light must follow the same rule. If a lamp is moving toward you and it emits light, the light should arrive slightly faster than if the lamp were standing still. If the source moves away from you, the light should arrive slightly slower. That is exactly how baseballs behave. So why would light behave any differently? But then physics ran into a puzzle. Light is not just a flying particle like a baseball. In the 19th century, scientists discovered that light is an electromagnetic wave. Waves normally need a medium to travel through. Sound waves travel through air. Ocean waves travel through water. Because of this, many physicists believe that light must travel through some invisible substance filling all of space. They called this substance the ether. The ether was imagined as a kind of universal background, an invisible cosmic air that carried electromagnetic waves across the universe. If this ether existed, then the Earth must be moving through it as our planet travels around the sun. And if we were moving through this cosmic medium, the speed of light should appear different depending on our direction of motion. Light moving along the direction of Earth's motion should appear slightly faster or slower than light moving sideways across it. In the late 19th century, two scientists, Albert Michelson and Edward Morley, designed a very sensitive experiment to detect exactly this effect. Their instrument could measure tiny differences in the speed of light depending on direction. According to the ether theory, they absolutely should have found a difference. But they did not. No matter how they rotated the apparatus, no matter what direction they measured, the speed of light always came out the same. The result was shocking. It meant the ether idea did not work. Light did not behave like a wave traveling through a medium the way sound travels through air. Something deeper was happening. Then in the early 20th century, a young physicist named Albert Einstein took the results seriously. Instead of trying to fix the ether theory, he proposed something far more radical. He suggested that the speed of light is not something that depends on the motion of the source or the observer at all. The speed of light is the same for everyone, no matter how fast they are moving. Imagine a rocket ship flying past Earth at an enormous speed, half the speed of light. The astronaut inside the rocket switches on a flashlight and sends a beam forward. If we use the baseball rule, we would expect the light to move at the speed of light plus the speed of the rocket. But according to Einstein, that does not happen. The astronaut measures the beam moving at exactly the speed of light. The observer on Earth also measures the beam moving at exactly the speed of light. Even someone moving in the opposite direction would still measure exactly the same number. This is the strange law at the heart of relativity. The speed of light does not add to anything. It does not care how fast the source moves or how fast the observer moves. Everyone measures the same value, about 300 million meters per second. At first, this sounds impossible. If speeds normally add together, how can light refuse to follow the rule? The answer is that the rule itself was incomplete. The universe is not obligated to follow our everyday expectations. When nature insists that the speed of light must remain constant, something else has to change to make the math work. That something turns out to be space and time themselves. The realization that the speed of light is always the same forced physicists to rethink the structure of reality. Distances and time intervals could no longer be absolute quantities that everyone agreed on. Instead, they had to stretch, shrink, and adjust depending on the motion of the observer. The universe protects the constancy of the speed of light by reshaping space and time around it. And once you begin to see that, you start to realize that light is not just another moving object like a baseball. Light is telling us something fundamental about the geometry of the universe itself. Now we can begin to see the deeper meaning behind this strange number we call c. Most people think of it as simply the speed of light, a very large velocity that light happens to travel at. But that description is actually misleading. The constancy of c is telling us something far more profound about the structure of reality itself. If c were just the speed of a particle, then like the baseball, it should change when the source moves or when the observer moves. You should be able to add your own motion to it, subtract from it, or even chase after it. But the universe refuses to allow that. No matter how you move, no matter how fast you go, you always measure the same value. This strange behavior forces us to reconsider what the number c really represents. Think about what a speed actually is. Speed is distance divided by time. When we say a car travels 100 kilometers per hour, we are connecting two different kinds of measurements: kilometers of space and hours of time. Speed is a conversion between those two quantities. Normally, that conversion depends on the motion of the object, but the speed of light behaves differently. Everyone may disagree about the distance light traveled. Observers moving relative to each other may also disagree about how long the journey took. Yet when they divide their distance by their time, the answer always comes out to the same number c. That means the universe is adjusting space and time so that their ratio always remains constant. This leads to a radical conclusion. The number c is not really the speed of light in the ordinary sense. Instead, it is a fundamental conversion factor between space and time themselves. It tells us how many meters of space correspond to 1 second of time. In other words, it acts like a ruler that measures both space and time using the same scale. Once you understand this, the world begins to look very different from the one we imagined before Einstein. For centuries, scientists believed space and time were separate things. Space was the stage on which events happened, a three-dimensional box stretching in every direction. Time was the ticking clock hanging on the wall of that box, flowing forward at a steady rate for everyone everywhere. According to that picture, the universe had a rigid geometry that never changed. But the constant speed of light shows that this picture cannot be correct. If the speed of light must remain fixed for all observers, then space and time cannot be independent quantities. They must be part of a single unified structure. Einstein realized that the universe is better described as a four-dimensional fabric called space-time. Instead of three dimensions of space and a separate dimension of time, we have one combined geometry where space and time can mix with each other. When an observer moves very fast, the coordinates of space and time adjust so that the speed of light remains constant. Distances may contract, time intervals may stretch, but the deeper geometry stays consistent. To understand why this happens, imagine two observers moving relative to each other. One observer measures a flash of light traveling across a certain distance in a certain time. The second observer is moving while the light travels. So from their perspective, the distance is different. If space and time were absolute, the speed would change. But the universe does something remarkable. Instead of letting the speed change, it reshapes the measurements themselves. The moving observer experiences time running differently and distances appearing different so that the ratio between them remains exactly c. This idea can feel very strange because our everyday experiences happen at speeds far below the speed of light. In daily life, the adjustments of space and time are so tiny that we never notice them. The classical rules of adding velocities work well enough for cars, airplanes, and even rockets moving thousands of kilometers per hour. But when objects move at a significant fraction of the speed of light, the hidden geometry of space-time begins to reveal itself. At that point, the number c stops behaving like an ordinary speed and begins to act more like a fundamental property of the universe. It becomes the scale that ties together the dimensions of space and time. Just as a meter converts between different distances, c converts between seconds and meters within the structure of space-time, and once you see c in that way, light itself begins to look different. Light is not simply a fast object racing across the universe. Instead, it moves exactly along the lines where space and time balance each other perfectly. Light is the phenomenon that reveals the underlying geometry of space-time. Now that we understand that c is not simply the speed of light, but a fundamental property of space-time, we can ask a deeper question. Why does this number appear everywhere in physics? Why does nature seem to guard this value so carefully? The answer is that c is not merely the speed of a particular phenomenon. It is the ultimate speed at which cause and effect can propagate through the universe. In other words, c is the speed limit of causality. To understand what that means, imagine that something changes somewhere in the universe. Perhaps a star suddenly explodes, or perhaps an atom emits a photon. That change cannot influence the rest of the universe instantly. Information about the change must spread outward through space. There's a maximum rate at which this information can travel, and that rate is exactly c. Nothing that carries information, influence, or causation can move faster than this limit. If something could travel faster than c, it would allow effects to appear before their causes in some reference frame, which would break the logical structure of physics itself. The universe avoids that contradiction by imposing a strict rule: no signal, no force, and no piece of information can travel faster than c. This rule applies not only to light, but to every interaction in nature. Even gravity obeys this limit. For a long time, physicists believed gravity might act instantaneously. According to Newton's theory, if the sun were suddenly removed from the universe, the Earth would immediately lose the gravitational force that keeps it in orbit and would fly off into space at once. In that picture, gravity had no delay. The force simply acted across distance instantly. But Einstein's theory of general relativity changed that understanding completely. In Einstein's view, gravity is not a mysterious force pulling objects toward each other. Instead, it is a curvature in the geometry of space-time itself. Massive objects like the sun warp the space-time around them, and planets follow paths within that curved geometry. If the mass changes, the shape of space-time must change as well. But that change cannot happen everywhere at once. The information about the change must travel outward through space-time. So imagine the sun suddenly vanishing. According to modern physics, the Earth would not notice immediately. For about 8 minutes, everything would appear completely normal. The Earth would continue moving along the same curved path it was already following. During those 8 minutes, sunlight would still be arriving at Earth because the photons that left the sun earlier are still traveling through space. Only after those 8 minutes pass would the sky suddenly go dark and the gravitational curvature disappear. At that exact moment, the Earth would stop following its orbit and begin moving in a straight line through space. The reason both the light and the gravitational influence arrive after the same delay is that they propagate through space-time at the same fundamental speed c. Gravity does not move faster than light, and it does not move slower either. Both are limited by the same universal constant. In recent years, physicists have even measured this directly. Enormous instruments called gravitational wave detectors have observed ripples in space-time produced by massive cosmic events such as colliding black holes. These detectors measure distortions in space-time that travel across the universe like waves on the surface of water. When scientists analyze the signals, they find that these gravitational waves travel at the speed c. The geometry of space-time itself changes and propagates through the universe at exactly the same speed as light. This tells us something very important about the meaning of c. The number is not really about light at all. We only call it the speed of light because light was the first phenomenon where humans measured it accurately. In reality, c is the speed at which the structure of space-time communicates changes from one place to another. It is the speed at which the universe updates its own geometry. You can imagine space-time as a vast elastic fabric stretching across the cosmos. When something changes in one region of that fabric, the disturbance spreads outward like a ripple. The stiffness of that fabric determines how fast the ripple moves. In the universe, the stiffness of space-time sets the maximum propagation speed, and that speed is c. Light happens to move exactly at this limit because photons have no mass. Massive objects require energy to accelerate and cannot reach the ultimate speed limit. But photons are different. They carry energy but no rest mass. So they naturally move along the boundary defined by c. And this is why light occupies such a special place in physics. It is not just a fast traveler crossing the universe. It is a phenomenon that moves precisely at the maximum speed allowed by the structure of space-time itself. The behavior of light reveals the fundamental rule governing how information, force, and causes propagate through reality. To understand what really happens when something moves close to the speed of light, we need to follow an idea that began in the mind of a teenager. When Albert Einstein was 16 years old, he asked himself a strange question. What would it look like if I could run alongside a beam of light, imagine chasing a light wave through space, and eventually catching up to it? If you could match its speed, the wave should appear frozen in front of you, like an ocean wave that stops moving when a surfer travels at exactly the same speed as the crest. The electromagnetic fields would form a static ripple hanging in space. But here's the problem. Maxwell's equations, the laws that describe electricity and magnetism, do not allow a frozen light wave. The mathematics says a light wave must move at the speed c. It cannot stand still. Einstein realized this contradiction meant something about our understanding of space and time had to change. To explore the problem, we can imagine a simple experiment inside a fast rocket. Picture a spacecraft traveling through space at 90% of the speed of light. Inside the rocket, everything appears completely normal to the astronaut. The clock on the wall ticks steadily. A cup of coffee pours smoothly into a mug. The astronaut's heartbeat feels perfectly ordinary. According to the principle of relativity, constant motion cannot be detected from inside the system. If you are moving at a steady velocity, the laws of physics around you look the same as if you were standing still. But now imagine an observer watching the rocket from Earth with a powerful telescope. From that observer's perspective, something strange happens. The astronaut inside the rocket appears to move more slowly. The motion of lifting the coffee cup looks sluggish. The ticking of the clock seems stretched out. Each second inside the rocket takes longer when measured by the observer on Earth. It is not that the clock mechanism is damaged or that the astronaut is tired. Time itself is running at a different rate. To see why this must happen, physicists use a very simple model called a light clock. Imagine a clock made from two mirrors facing each other with a photon bouncing between them. Each time the photon travels from one mirror to the other and back, we count one tick of the clock. If the clock is at rest relative to you, the photon simply moves straight up and down between the mirrors. The path is short and regular, and the time between ticks is consistent. Now, imagine that this light clock is inside the fast rocket, moving sideways relative to an observer on Earth. From the astronaut's point of view, the photon still moves straight up and down between the mirrors, but the observer on Earth sees a different path. Because the rocket is moving sideways while the photon travels, the photon must follow a diagonal path between the mirrors. The photon is chasing the moving mirror on the way up and then catching the lower mirror on the way down. That diagonal path is longer than the straight path seen by the astronaut. Here is the crucial point. The speed of light must remain constant for both observers. The photon cannot travel faster just to compensate for the longer path. If the distance is longer and the speed stays the same, the time required for the photon to complete each bounce must increase. That means the ticking of the light clock appears slower to the observer on Earth. This effect is called time dilation. Time itself stretches for objects moving close to the speed of light. The mathematics describing this effect contains a factor that grows dramatically as velocity approaches c. At 90% of the speed of light, the moving clock runs a little more than twice as slow compared to the stationary observer. At 99%, the difference becomes far more dramatic. A traveler moving extremely close to the speed of light could experience a short journey while many years pass for people who remain behind. But relativity does not only affect time. Space itself changes as well. When an object moves at high speed, the length of objects measured along the direction of motion becomes shorter from the perspective of a stationary observer. This effect is called length contraction. The faster an object moves, the more the distances in the direction of travel appear compressed. Time stretching and space shrinking are not separate phenomena. They are two sides of the same geometric adjustment that preserves the constant value of c. The universe rearranges measurements of time and distance so that the speed of light remains unchanged for every observer. And when you push this logic to its ultimate limit, you reach the extreme case of light itself. For anything with mass reaching the speed of light is impossible. But photons already move at that limit. In that situation, the dilation of time becomes infinite and the contraction of distance becomes complete along the direction of motion. From the perspective of the photon, the interval between its emission and its absorption collapses. Time does not advance and the distance ahead disappears. This strange conclusion is the doorway to the deeper idea we started with. Motion is defined as traveling a certain distance during a certain amount of time. But if the time experienced by light does not pass, and the distance along its path collapses, the journey itself takes on a very different meaning. To really understand why the journey of light collapses in this strange way, we need a different kind of map. Not a map of countries or oceans, but a map of reality itself. Physicists draw this map using two axes. On the horizontal axis, we place space. That represents distance across the universe. On the vertical axis, we place time. That represents the sequence of moments from past to future. When we draw events on this diagram, we create what is called a space-time map. Each point on the map represents something happening at a particular place and a particular moment. For a long time, people imagined the universe like a stage. Space was the stage and time was the clock that moved events forward across it. But Einstein and the mathematician Hermann Minkowski realized that this picture was incomplete. Space and time are not separate backgrounds. They are woven together into a single four-dimensional structure called space-time. Instead of imagining the universe as a movie playing frame by frame, we can imagine it as a complete geometric object, something like a giant four-dimensional block. Every event that ever happened and every event that ever will happen exists somewhere inside that block. You can picture your own life as a line drawn through this structure. One end of the line represents the moment you were born. The other end represents a moment far in the future. Each point along that line corresponds to where you were in space at a certain time. What we experience as the present moment is simply the place where our awareness moves along that line. But in the geometry of space-time, the entire line already exists. Now let us add light to this map. Because the speed of light is constant, we can measure distance in units that match time. 1 light year is the distance that light travels in 1 year. That means on our space-time diagram, a beam of light always moves 1 unit of space for every unit of time. When we draw that motion, it forms a line at a 45-degree angle across the map. If light moves forward, it travels along one of these diagonal lines. These lines form a structure called the light cone. Imagine standing at one event on the diagram. All possible light rays that leave that event form a cone spreading into the future. Everything inside that cone represents events that can be influenced by the original event because a signal moving at or below the speed of light could reach them. Everything outside the cone lies beyond the reach of that event. Signals cannot travel fast enough to connect them without breaking the speed limit of causality. So the light cone divides the universe into regions of possible influence. But something even deeper hides in the geometry of space-time. In ordinary geometry, we measure the distance between 2 points using the Pythagorean rule. If you move 3 units east and 4 units north, the straight line distance is 5 units. We square the distances along each direction and add them together. Space-time follows a different rule. When physicists calculate the separation between 2 events in space-time, they do not add space and time in the same way. Instead, they subtract one from the other. The formula involves time squared minus distance squared. That minus sign may look like a small detail, but it completely changes the geometry of reality. Time and space do not reinforce each other the way 2 spatial directions do. They partially cancel each other. Now consider what happens along the path of light. For a photon, the distance it travels through space is always exactly equal to the distance it travels through time when measured in these units. 1 light year of space corresponds to 1 year of time. When we insert those values into the space-time distance formula, something remarkable occurs. The time-squared term and the space-squared term cancel each other perfectly. The result is 0. This means that in the geometry of space-time, the separation between the emission of a photon and its absorption has 0 length. Physicists call this a null interval. The path followed by light is known as a null geodesic. A geodesic is simply the straightest possible path in a curved geometry. For light, that straight path has a space-time length of 0. This is the geometric reason behind the statement that light does not move in the usual sense. From our perspective, the photon travels across enormous distances and through long stretches of time. But in the deeper geometry of space-time, those 2 quantities cancel each other along the light path. The starting event and the ending event lie on a connection whose interval is 0. In other words, the photon traces a line through space-time that has no length according to the rules of Minkowski geometry. The emission of the photon and its absorption are connected by a bridge that collapses distance and time into a single relation. What appears to us as a long journey across the universe becomes, in the deeper structure of space-time, a direct connection between two events. Now we have seen the geometry that explains why the interval along the path of light is zero. But geometry alone does not tell us how light actually behaves when it travels from one place to another. To understand that part of the story, we need to move from relativity into quantum physics. In the quantum world, light does not behave like a smooth wave spreading through space the way people once imagined in the 19th century. When detectors measure light carefully, they find something surprising. Light arrives in tiny individual packets called photons. Instead of a continuous stream, it comes in discrete clicks, one photon at a time. This means that when a photon leaves a source and eventually reaches a detector, we have to ask a very strange question. How did that photon decide which path to follow? Our everyday intuition suggests the photon simply takes the straight line from the source to the detector. That seems obvious because when we shine a flashlight, the beam appears straight. But quantum electrodynamics, the theory that describes the interaction between light and matter, tells a very different story. According to QED, a photon does not choose a single path. Instead, it explores every possible path through space-time. It can go straight, it can curve, it can wander off in wildly complicated directions. In principle, it can even travel to extremely distant regions of space and still contribute to the final result. The photon behaves as if it considers all possible routes connecting the starting point and the ending point. To calculate what actually happens, physicists use a mathematical idea introduced by Richard Feynman. Instead of thinking about a particle moving along one trajectory, we assign a quantity called a probability amplitude to every possible path. These amplitudes can be visualized as little arrows pointing in different directions. Each path from the source to the detector carries its own arrow. When we want to know the probability that the photon arrives at the detector, we add all these arrows together. The direction of each arrow depends on how long the photon would take to travel along that particular path. The longer the travel time, the more the arrow rotates before it reaches the detector. For paths that are very long or extremely twisted, the rotation becomes rapid. Even a tiny change in the path length causes the arrow to rotate by a large amount. When we add the arrows from many nearby paths, they tend to point in different directions and cancel each other out. One arrow may point to the right while another points to the left, and the sum becomes almost zero. Now consider the paths that lie close to the straight line between the source and the detector. These paths are special because small changes in their shape do not significantly change the total travel time. When the travel time remains almost the same, the arrows corresponding to these paths rotate by nearly the same amount. Instead of canceling each other, they line up in roughly the same direction. When we add them together, they reinforce each other and create a large combined arrow. The probability of detecting the photon is determined by the length of that final arrow, because the arrows near the straight path reinforce one another, while the arrows from more complicated paths cancel out. The straight line emerges as the path with the highest probability. This is why light appears to travel in straight lines, even though the quantum description allows every possible path. This principle is closely related to a classical rule known as the principle of least action. In optics, it also appears as the principle of least time. Light tends to follow the path that makes the travel time stationary relative to nearby alternatives. In quantum mechanics, this rule emerges naturally from the interference of probability amplitudes. The straight line is not chosen by the photon in a deliberate sense. It simply survives the cancellation process while other possibilities fade away through destructive interference. Now connect this quantum picture with the geometric picture we discussed earlier. In relativity, the path of light through space-time has a null interval, meaning the separation between emission and absorption is zero in the Minkowski geometry. In the language of quantum theory, the phase associated with a photon's amplitude becomes stationary along this path. Because the phase does not vary rapidly for nearby trajectories, the corresponding arrows align and reinforce each other. The geometry of space-time and the interference of quantum amplitudes both point toward the same conclusion. The photon does not behave like a tiny bullet flying through space. Instead, it behaves like a connection established between two events in space-time. The emission of the photon and the detection of the photon form the endpoints of that connection. Quantum amplitudes explore every possible route between those endpoints, but only the paths compatible with the geometry of space-time contribute significantly to the final outcome. The straight line that we observe is the visible trace of this deeper quantum process. Seen from this perspective, the motion of light becomes something more subtle than ordinary travel. The photon does not simply move from point A to point B in the classical sense. Rather, it represents a quantum relationship linking the emission event and the absorption event within the structure of space-time itself. Now, we can bring all of these ideas together and see what they imply about the nature of light. Geometry told us that the path of light through space-time has a null interval. Quantum theory told us that a photon behaves like a connection formed by probability amplitudes between two events. When these pictures are combined, they lead to a remarkable way of thinking about emission and absorption. Instead of imagining light as something that leaves a source and then later arrives at a detector, we can think of the two events as parts of a single interaction. In this view, the emission of the photon and its absorption are not completely independent processes separated by time. They are two ends of the same physical exchange. This idea was explored in the 20th century by John Wheeler and Richard Feynman in what is known as absorber theory. The central insight of this theory is simple but deeply counterintuitive. A charge does not emit radiation unless there is something in the universe capable of absorbing that radiation. The emission and the absorption form a complete transaction. The process only makes sense when both ends exist. You can think of it like pushing a stick forward with your hand. You do not feel any resistance until the far end of the stick touches a wall. The push from your hand and the resistance from the wall appear together as one connected event. Without the wall, the push would produce no force in return. Apply this picture to a photon traveling through space. When an electron in a star releases energy in the form of a photon, we usually imagine that the photon begins a long journey through empty space. Perhaps it travels for millions or even billions of years before eventually striking a detector or an eye. But if the space-time interval along that path is zero and the photon experiences no passage of time, the emission and the absorption are linked more directly than our intuition suggests. In the geometry of space-time, those two events lie on a connection that has no length. From the perspective of the photon, the two moments occur together. This does not mean that the future sends signals backward in time in the everyday sense. Instead, it means that the full description of the process includes both the emitter and the absorber as parts of one consistent solution to the equations of physics. The electromagnetic field connects them across space-time in a way that respects the speed limit set by c. The photon becomes the mediator of that exchange, a kind of handshake between two pieces of matter separated by distance. When we think in this way, the idea of distance begins to change meaning. For objects with mass like ourselves, distance is a real barrier. We must spend time and energy to cross it. But for the interactions carried by fields, the geometry of space-time allows connections that are much more subtle. The photon does not slowly crawl across the universe the way a spaceship would. Instead, it exists along the entire null path, linking its beginning and its end. The emission event and the absorption event are tied together by that path like 2 points joined by a thread in the fabric of space-time. Modern physics has revealed other examples where this deep connectivity appears. In quantum entanglement, two particles can share a single quantum state even when separated by enormous distances. Measuring one particle instantly determines the outcome for the other. This phenomenon does not allow faster than light communication, but it shows that the structure of reality is more interconnected than our everyday experience suggests. The correlations exist because the particles are part of one unified system described by the same quantum state. Light provides another window into that interconnected structure. When you detect a photon that left a distant star long ago, you are not merely receiving a traveler that wandered through space for ages. You are completing a process that links your detector with the event that created the photon. The emission and the absorption form a closed interaction within space-time. The photon is the exchange that balances energy and momentum between the two locations. Seen from our human perspective, the story still looks like a journey. We see the photon leave a star and later arrive at Earth after crossing enormous distances. But from the deeper viewpoint of space-time geometry and quantum mechanics, the process is closer to a connection than a voyage. The photon defines a relationship between two events, rather than a path taken by a tiny object moving step by step. This is why the statement that light does not move carries a deeper meaning. It does not deny that light travels across the universe according to our measurements. Instead, it reveals that at the fundamental level, light represents the link that joins separated events into a single physical interaction. The photon is the handshake between matter across space-time. The universe does not send little messengers racing through emptiness. It establishes connections that tie distant points together within its geometry. In that sense, light does not simply travel through the universe. Light connects.